Grizzly. There's Grizzly. Say hi, Grizz. Did you say hi? We are going to start talking about equilibrium. So equilibrium is where things end up, essentially. So if we talk about kinetics, we talk about how fast a process takes place. And if we talk about equilibrium, we are talking about when a process stops changing. So we will make sense out of that as we go through. So the equilibrium state is reached when the concentrations of reactants and products remain constant over time. So we're going to look at a reaction. And for a while, the concentrations might be changing, but they're going to reach a point at which they're at the best concentration and they'll stop changing. So this is just the picture of this particular reaction. So the brown color is the product, the nitrogen dioxide. So you can see where equilibrium is based on the color, essentially. So we have this reaction of N2O4 is in equilibrium. So now rather than an arrow going in one direction, we're always going to put these double arrows. That means the reaction goes forward, but they'll reach a point at which it doesn't change any longer. So you generally don't get all products. You get a mixture of the reactants and the products. So this is just a picture or a couple of graphs showing you that in this particular reaction, doesn't matter what you start with. So on the left-hand side, we started with N2O4, and so its concentration is decreasing, the blue line, where the product's concentration is increasing. You reach a point, it looks like maybe right about here, where the concentrations stop changing and they both just plateau out. So we're on this side, we are starting out with NO2. So we're starting out with the product. And so now its concentration, the pink line, is going to be decreasing with time, whereas now the N2O4, the reactant, is going to be increasing. So really, when you think about these double arrows, we want to stop thinking about reactants and products because the reaction can go forward and it can go backwards. And so in each case, we'll look at this point at which the concentration stopped changing. So on both sides, you can see the concentration stops changing for N2O4 when it's about, maybe 0.035. And same thing over here. And the concentration of NO2 is maybe about 0.015. So we'll see in a second that the ratio is going to be what stays constant. So as the N2O4 is consumed, the rate of the forward reaction goes down, because remember from what we learned in our kinetics chapter, the rate of a reaction is dependent on the concentration of the species present, and the rate changes as that concentration changes. So as the rate forward is going down because N2O4 is going down, the rate backwards is going up because NO2 is being created, and so its concentration is getting larger. So the rate forward is going to reach or equal the rate backwards when we reach equilibrium. This is just the data that would have gone in to making those graphs. No, this isn't the going into the graphs. It's more looking at this right here. The fact that the concentrations, no matter where you start with reactant or product, the concentration ratio ends up being the same. So in this particular case, we're going to see in a second that it's always the concentration of the products raised to their stoichiometric coefficient divided by the reactants raised to their stoichiometric coefficients. That's what reaches a constant when you reach equilibrium. And so on the far right-hand side, they're showing you that it doesn't matter which experiment you start with, all reactant, all product, all reactant, all product, sum of each. You're going to reach a point where that ratio, the product concentration squared, because the stoichiometric coefficient is 2, divided by the concentration of the reactant to its stoichiometric coefficient, which is 1, that ratio is going to reach a constant. So for a general reversible reaction, so the reaction has to be able to go forward and backwards. So if we think back like to our radioactive decay, those processes aren't reversible. They go in one direction and the process doesn't reverse. So this is only true, this idea of equilibrium, if you're talking about reversible processes. So A and B can go to C and D, but C and D can also react backwards to make A and B. So the equilibrium constant, so that ratio that's going to be equal to a constant, is always going to be the products raised to their stoichiometric coefficients divided by the reactants. And so if you take upper level physical chemistry, you'll get a little better understanding why it's that particular ratio. It comes really out of kinetics and the rate forward equaling the rate backwards. So this is just showing you how you would work through that data, how you would take the ratio in each and every experiment, the concentration of NO2 at equilibrium squared, divided by the concentration of N2O4. And in each case, we get the right-hand column where all those numbers should be the same, but clearly there's a little bit of experimental error, which is what you would expect if you're measuring concentrations. So the equilibrium constant for different processes, the top reaction, you have nitrogen and hydrogen forming ammonia, NH3. So the equilibrium constant would be the NH3 squared divided by nitrogen and then H2 to the third power. So if you wrote the reaction in the backwards way, you'll see that the expression is just 1 over the expression for the first reaction. So the second reaction is the same exact reaction. We've just written it as if the ammonia is the reactant and the nitrogen and the hydrogen are the products. So Kc prime, the equilibrium constant for this second reaction, is just going to be 1 over Kc, the equilibrium constant for the first reaction. And then for the next one, you see that all that changes from reaction 1 to 3 is that we multiply everything by 2. And so that means Kc prime prime. So the Kc for this particular reaction, the third one. If you compare it back to the second one, it's going to be the same expression, products over reactants, as the first equation. But now everything is multiplied by 2, so that means your equilibrium constant would have to be squared for the 2 to be equal. So the equilibrium constant for the first reaction squared equals the equilibrium constant for the third reaction. You could also write the equilibrium constants in terms of pressure. They'll have different units. And so a different numerical value, but we know that pressure is proportional to concentration if you have gases. So if you have gases, you can write an equilibrium constant in terms of concentration or in terms of pressure. And this shows you an equation. I'll show you where this comes from in class. I don't particularly like this equation. I kind of like doing a conversion of each specific reaction, which is what I'll show you. All it's showing you is that Kp and Kc are related. So if you have gases and you have perfect gases, we can use PV equals nRT, and we can use that equation to relate concentration to pressure, and that's how you come up with this first equation here. If we have a reaction that has solids or liquids in it, the only thing that's going to go in the equilibrium constant are the gases. So in this case, if you think about it, the concentration of calcium carbonate, limestone, if it's a solid chunk of it, is really just its density. And so its concentration doesn't change as the reaction takes place. Same thing is true for the calcium oxide. The concentration doesn't change because it's really just equal to the density and some conversions between density and concentration. So the only thing that you'd include in this equilibrium constant when you have heterogeneous equilibrium is just the pressure of CO2 or the concentration of CO2. So pure solids and liquids are not included, and that's because their concentration really remains constant, even if some of it reacts, because it's based on that chunk that you have in there. This is just talking about that exact idea, heterogeneous equilibrium. As long as you have some of the solid in the container, its concentration or density isn't changing. And so all you have to do is include the gas pressure or concentration. So if we want to use the equilibrium constant, we're going to spend really 3 chapters dealing with this. We're going to go in great depth into acid-base chemistry and equilibrium constants for those reactions. And then the very last chapter we're going to talk about electrochemistry, which is how you get electrical work out of chemical reactions. And in both cases, we'll just practice this idea a lot. So really getting the fundamental concept in this chapter is really important because we're going to apply it to different chemical systems. So this just shows you that depending on the equilibrium constant's value, it tells you whether or not you have mostly product or mostly reactant. So for example, in the top reaction, water forming hydrogen and oxygen, if the equilibrium constant is 10 to the minus 48, essentially that says you have very, 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 very little product when you reach equilibrium, and you have mostly all reactant because that ratio is such a small number. If you look on the lower left-hand corner, you have an equilibrium constant that's moderate, it's 57. So that means the ratio has a significant amount of both reactant and product in order to get it equal to 57. But then if we look at the bottom right-hand corner, it's just the reverse reaction of above. So the equilibrium constant for it should be 1 over our equilibrium constant that's for this reaction up at the top. But what it shows you is that if you are thinking about the reaction of hydrogen and oxygen forming water, you should pretty much have all water at equilibrium because the equilibrium constant is 10 to the 47th. So the ratio of water squared divided by hydrogen squared times oxygen pressure, or concentration in this case, they're giving you a Kc, it's going to be 10 to the 47th. Pretty much says there's no reactants left over. So oftentimes we can think about a reaction quotient as a way to figure out will the reaction go forward or backwards to reach equilibrium. So if we know the K for a reaction, and if we calculate the expression for K, but with any random concentrations, so let's say you mix some C, D, A, and B, and you're not necessarily at equilibrium, if you calculate the ratio as if it was in an equilibrium expression, if Kc is bigger, or if Qc is bigger than Kc, then you need the numerator to get smaller or the denominator to get bigger. And so the reaction will go backwards. And if the opposite is true, the reaction will go forwards. And if you just happen to mix the right quantities and Kc equals K or Qc, then the reaction is at equilibrium. So here's what I just said. So if Qc is less than Kc, the reaction has to go from reactants to products. So we will want to make this expression bigger if it's smaller. And the way you make it bigger is make the numerator bigger or make the denominator smaller. Kc greater than, or Qc greater than Kc, it's going to go from right to left, so products to reactants. And if they're equal, then the reaction is at equilibrium. This is just a more visual way to look at that, and it's not a new concept. It's just looking at which is bigger and therefore which way the reaction will go. So this is a problem where we have some HI, so we have some product and we add it to a container and it comes to equilibrium, and we want to calculate the equilibrium concentrations of each of the species. So we'll set up the equilibrium expression. Let's just go through this. This is the flow chart that your book has, and you're welcome to use it if you want, but I think it's pretty logical what we're going to do. So we put some HI in. We have no reactants, no hydrogen and iodine gas. And so we need to set up the expression for Kc and see how the concentrations will change in order for the reaction to reach equilibrium. So we start out, this is called an ice box. So initially we have 0 moles of H2, 0 moles of I2, and 0.250. And I don't think, no, we're not talking about moles. Now we're talking about molar concentration. So if you have 0.5 moles of HI and you put it in a 2-liter container, then the molar concentration moles per liter is going to be half that. And so we start out with 0.250 molar in the product. It's going to change. So that's the C in the icebox. H2 has to go up. I2 has to go up. HI has to go down 2 times for every 1 time the others go up. So if you think about it, it takes 2 HIs to make 1 I2. So you have to subtract 2 times whatever your X is if you've defined your X to be how much I2 and how much H2 are made. So that means at equilibrium, we'll have X and X for H2 and I2, and we'll have where we started, 0.250 minus 2X. So if we set up the equilibrium expression, it's going to be the concentration of HI squared divided by the concentration of H2 times the concentration of I2. We were told that our equilibrium constant is 57. So 57 equals the concentration of the HI at equilibrium squared divided by the concentration of H2 times I2. So that ends up giving you X squared. And you can solve this one quite easily because if you notice, you can take the square root of both sides. So when you take the square root of both sides, for X, you get 0.0262. And we're going to practice using Mathematica to solve equations like this. We might sometimes need the quadratic, sometimes it may be a cubic. So we will practice Mathematica can solve this sort of problem really easily. So if X is 0.0262, that means that the concentration of H2 is 0.0262 molar at equilibrium. I2 has the same concentration. HI at equilibrium is what we started with, 0.250 minus 2 times the X we solved for. So what should be left is 0.198 molar. This just shows you a reaction that must be the ammonia. Yeah, making NH3 from H2 and N2 and what the setup looks like. It's a very, very, very important industrial process. We use NH3 as a fertilizer. So we're going to now think about if a reaction comes to equilibrium and we stress it somehow, how will the reaction relieve that stress? So if the concentration of reactants and products can be changed, these are ways you can stress it. The concentration of reactants or products could be changed, so you might add more of one or the other. You can change the pressure and the volume, and you can change the temperature. And when those things happen, let's think about what happens. So this shows you after the pink region that we are going to stress it by adding some N2. And when we add the N2, what has to happen? So in the pink region, the reaction's at equilibrium. All those concentrations are constant. When we add the N2, now the reaction wants to relieve the stress. So it wants to get rid of some of that N2. And in order to do that, it has to react to the right. When it does that, it has to use up some H2. So H2 has to go down. And then H3 has to go up because as you're reacting it with this added amount of N2, you're going to the right. So this shows you that if you add a reactant, the reaction needs to adjust by reacting forward. You could also use a Q for the same exact kind of idea. So when you've added the N2, then the Q will get smaller because N2 is in the denominator. Therefore, the reaction has to go forward. So when it's at equilibrium, Q equals K. When we've added a reactant, Q becomes smaller than K. And so they'll be establishing a new equilibrium by reacting forward. So in general, when an equilibrium is disturbed by the addition or removal of any reactant or product, Le Chatelet's principle predicts that the concentration stress of an added reactant or product is relieved by net reaction in the direction that consumes that added substance. And the concentration stress of a removed reactant or product is relieved by net reaction in the direction that replenishes the removed substance. So you could change the concentration of reactant or product by adding more or by subtracting some. But notice, we're not talking about the K changing, so K stays the same. And the reaction relieves the stress by reacting forward or backwards in order to come back to the situation where Q equals K. So we're not changing K when we change the concentration of a reactant or a product. So here is just a reaction. The mixture is at equilibrium, and it tells you how much of each species is present. It's disturbed by increasing the concentration of N2 to 1.50. So you can immediately see that Q is less than Kc. So we've added more reactant. The reactant goes into the denominator. So Q is going to be less than K at this point. So more reactants will be consumed and the reaction will go from left to right. This is just showing it in a visual, because if you have a reaction where the compounds are colored, either reactants or products, you'll be able to see that change visually. Changes in the pressure and volume. So if we have a mixture and we're at equilibrium on the far left, and if we increase the pressure, that means we decrease the volume. So they've pushed the piston down. The mixture is no longer at equilibrium, and the net reaction occurs from reactants to products, decreasing the number of molecules until equilibrium is reestablished. So if you want to think about it, if you increase the pressure, it wants to relieve that pressure. It will react in the direction where you have fewer moles of gas, because that's the side that decreases the pressure. So it's going to go from reactants to products, because there'll be a lower pressure if you have more NH3 and not as much N2 and H2. In general, when an equilibrium is disturbed by a change in volume that results in a corresponding change in pressure, Le Chatelet's principle predicts that if you increase the pressure by reducing the volume, you'll bring about net reaction in the direction that decreases the number of moles of gas, and a decrease in pressure by expanding the volume will bring about net reaction in the direction that increases the number of moles of gas. And if you do either of these, increase or decrease the pressure, but you have equal stoichiometry, so let's say you have 1 mole of gas goes to 1 mole of gas, then the reaction has no options for alleviating the stress, and it will stay as it is. It won't react forward or backwards. Okay, so this is just showing you this mathematically. So we have this solution, gaseous solution. We have the same molarities. We disturb it by reducing the volume by a factor of 2. So let's see where they show you that. Yeah, so if you decrease the volume, remember that each of these is divided by volume, the concentrations. So you have, if you're reducing the volume and making it smaller, then that ratio becomes smaller than Kc. And if Q is smaller than Kc, more reactants will be consumed and the reaction will go from left to right. So now if we change the temperature, we have to know a little bit more about the reaction. We have to know whether or not it's endothermic or exothermic. So it's easy just to think about that if the reaction is exothermic, that essentially means that heat is a product. So if you raise the temperature, you're adding heat to the system, which will force the reaction to go back to reactants. And in this case, you're actually changing the value of the K. You're not just shifting the equilibrium so that it becomes K again, but now the value of K changes with temperature. So in general, when an equilibrium is disturbed by a change in temperature, Le Chatelet's principle predicts that the equilibrium constant for an exothermic reaction decreases as the temperature increases, because as I said, if heat is a product in an exothermic reaction, you're going to force the reaction back towards the reactant side, and so the numerical value of the rate constant will get smaller. And if the equilibrium constant for an endothermic reaction, it's going to increase as the temperature increases, because now your heat would be a reactant. And so as you add heat, wants to alleviate that stress, it's going to force the reaction to go forward, and therefore you'll have more products over fewer reactants, and that means that the value of equilibrium constant will increase as the temperature increases. Changes in temperature, this is just showing you the same reaction that we looked at the beginning where the product is brown. So if you have it in an ice bath versus room temperature, you can see the difference in color. So there's more product when it's warmer, and that's because delta H is greater than 0, it shows you. So as you go from ice on the far left to just plain water on the far right, then or in this case, it looks like the water that's been heated up. So you go from low temperature to high temperature. If delta H is positive, then heat's a reactant, and so you're forcing the reaction to go to products. So you're going to see that darker color on the right because you're getting more NO2 at higher temperatures. So how does a catalyst affect equilibrium? It doesn't. The only thing it affects is how fast you establish equilibrium. So if you talk about reactants to products, we're going to see in one of our last chapters on thermodynamics that equilibrium is really a function of the physics difference between reactants and products. The only thing that happens if you add a catalyst is you'll take down the activation barrier between, and so the reaction will go faster forward and backwards. So equilibrium will be at the same concentration ratio, but you'll just establish it faster. And I guess that is all this chapter. So really focus hard on understanding this basic concept of equilibrium, because we are going to use it in lots of applications for several chapters, and it'll be much, much easier to think about applying it if you really understand this concept that equilibrium is where the concentration ratio stops changing. The reaction is still going forward and backwards. It's just that the concentrations are the ratio is staying constant because that rate of forward and backwards is the same. So if one molecule goes forward, another molecule goes backwards.